In this video, we're going to consider mathematical induction. We want to show how to prove something using mathematical induction. And suppose we wish to prove that a certain property of the natural numbers, call that Pn, some property of the natural numbers, maybe some inequality or something, is true for all n greater than or equal to m. In this case, m and n are natural numbers. And so we want to prove this property is true for all natural numbers greater than or equal to m. And we can prove this using mathematical induction. And the steps for induction are the following. We must show the following. So if we want to prove this property is true for all n greater than or equal to m, we have to show that it's true, the property is true for that first natural number that we want to show that it's true for our starting point. So this is called the basis step. The basis step. Prove that it's true for that first natural number n. And then we have to do the induction step. We're allowed to assume that this property is true for some given natural number n. And then show that it's true for n plus 1. And if you can show these two things, then the property is true for all n greater than or equal to m. Now, it's best to understand these problems by doing examples. And I'm going to do an example here. Now, this particular example isn't one that you would normally do or need to do by induction, but it'll kind of illustrate the concepts here. Let's do this example. Prove that n squared is greater than or equal to n plus 5 for all n greater than or equal to 3. And remember, this is a symbol for all n greater than or equal to 3. So do your proof. Again, you can either call it step 1 or the basis step. Usually I'll call it the basis step. And again, the basis step says we have to prove that it's true for that first value. So we want to prove that it's true for n equals 3. I'll put that in parentheses, just show where we're starting. So the question is it going to be true for that first value? So in other words, if we go up here and let's put a 3 in the left-hand side and a 3 on the right-hand side, the question is that inequality true for that? So on the left-hand side, we get 9. Right-hand side, we get 8. And yes, for our basis point, our first value, it's true. So we've passed that one. So next, let's do the induction step. And to remember from our induction step, we're allowed to assume that the property is true for n. And we want to show that it's true for n plus 1. So let's assume that this is true. And we want to show, a lot of times what I'll do, put in parentheses what we want to show. Want to show that it's true for n plus 1. So that means we have to replace n with n plus 1 in these cases. So we want to show that this is true for n plus 1 and plus 1 here. So we replaced n with n plus 1. And maybe just to see what we're headed for, what does this mean? We could even maybe simplify this just a little bit, just to get an idea what we want to, what we have here. Let me just multiply this out. If we square this, this would be n squared plus 2n plus 1. And the right-hand side, we'll have 1 plus 5 is 6. So we want to show this, which is the same as showing this. So usually when we do these kind of proofs, unless we're trying to prove that something's divisible by a number, usually you start with what you're allowed to assume. So begin with this n squared greater than n plus 5. And now we would like to match either the left-hand side or the right-hand side up here. That'll usually be a good place to start, is try to match one side or the other by adding something, subtracting something, maybe squaring both sides. So if we're beginning with this, probably the easiest thing would be to try to match the right-hand side. So let's add 1 to both sides. And so if we n squared plus 1. So all I did was add 1 to both sides, being with our assumption. Again, we're allowed to assume this was true. So if we just do play according to the rules, then we can assume this is true, because all I did was something you're allowed to do. You're allowed to add the same number to both sides. So what we want to show so far matches over here. Now we'd like to match this over here. But now, if this is greater than this, and we add a positive number to this side, it's going to remain greater. That's still going to be a true statement. In other words, if this is a true statement, and we add a positive number here, it's the inequality still going to be true. Now, if we added a positive number to this side, since this is already smaller, we can't know for sure if that's true. But over here, we can. If you have this bigger than this, and you add a positive number here, then this is still going to be true. And so what we'd like to do, we'd like to add 2n over here. And of course, since n is always greater than or equal to 3, 2n is always going to be positive. Add 2n, which is a positive number, to the left-hand side. N squared plus 2n plus 1 is greater than that. And that's what we were trying to show. We were trying to show that this was greater than that. So let's try to do a more complicated one. Another example. Prove that this is true for all n greater than or equal to 1. Now, first of all, let's understand what we have here. What does this really mean? First of all, let's maybe just do some scratch work just to understand. And so let me just do some, and maybe let me even do it on a separate sheet of paper here. So what does this mean? So if we have like n equal to 1, so if n was equal to 1, we would have 1 equal 1 squared. Put this over here like this. For n equal to 2, that means, again, this is actually the formula on the left-hand side. Like the left-hand side formula is 2n minus 1, but you're always adding that term. So we're going to have like 1 plus 2n. So it's going to be 4 minus 1, which is 3, equals 2 squared on the left-hand side. N equals 3. When you're doing that, you're adding another term plus 2n minus 1, n is 3. It's going to be 5. Right-hand side, you're going to have 3 squared. N equal 4 plus 1 plus 3. Again, then 2n minus 1. That's going to be 8 minus 1 is 7. And we're saying that that's equal to 4 squared. Now, you can actually check these. You can see that this is going to be 10, 15, 16. That's 16. This is going to be 5, 8, 9. That's 9. So that's the way these kind of progress. So just want to write that down just so we get an idea of how these work. And so let's do the proof using induction. So again, do the basis step. N equal 1. Again, we picked 1 because that's where we're starting up here. And so again, the question is this true? So for n equal 1, we're just going to have 1 term on the left. And is that going to be equal to 1 squared? I think we can pretty quickly say yes, that's true for the basis step. Now let's go to the induction step. And so again, for the induction step, we're allowed to assume that 1 plus 3 plus 5 plus 2n minus 1 equals n squared. We're allowed to assume that that's true. And then we want to show that it's going to be true for the next term. Now, in this case, remember, is we're kind of showing how things were progressing. On the left-hand side, that means we're going to be, when we go to n plus 1, we're going to be adding that term. So we want to show that 1 plus 3 plus 5 plus 2n minus 1. Then the next term is going to be 2 n plus 1 minus 1. So again, we went to that next term. But on the right-hand side, as you see, we do that next one, we just keep adding 1 to that. So that's going to be n plus 1 squared. So as before, begin with your assumption. And again, we're going to try to match. We're eventually going to try to show this up here. So once again, maybe try to match either the left-hand side or the right-hand side by maybe adding something. Now, it'll be difficult to add something to the right-hand side to get this, but it'd be pretty easy to add this to both sides to make this match. In other words, add 2n plus 1 minus 1 to both sides. So if we do that, so again, I started with this and added this term to the left-hand side. Let me also add it to the right-hand side. So be careful here. So now you see we've matched the left-hand side of what we want to show simply by adding, starting with our assumption, then adding this to both sides. Now the question is this side over here equal to what we want to show over there? So let's go to the next step. Again, sometimes you can just use like continuation marks, but I'll write the left-hand side out, since even though I'm not going to change anything there. And now notice over here we have, this is 2n plus 2 minus 1. So 2n plus 2 minus 1, that's going to be n squared plus 2n, then 2 times 1 is 2 minus 1. So that's what, plus 1. Like this. And now let's just bring this left-hand side down again. And let's factor this. Of course, this factors into n plus 1 times n plus 1, which is n plus 1 squared. So now we've matched what we wanted to show. We wanted to show that this is equal to this. That completes the proof. we went through our 2 steps. We went through the basis step, went through the induction step. And we were able to show that this worked for the basis step and it worked for the induction step. We were able to assume that the property was true for n and use that to show that it's true for n plus 1. So let's do another one. Show that two n is less than or equal to n plus 1 factorial for all n greater than or equal to 1. Let's do the proof and do your basis step. Again, this time n is going to be equal to 1. Again, based on what we're given up here. And so the question is, if you put 1 here, and you put 1 on the right-hand side, is the inequality going to be true? So this is going to be 2. And this is 2 factorial. Of course, 2 factorial is 2 times 1, which is 2. So yes, 2 is less than or equal to 2. So now do the induction step. Again, assume that 2n plus 1 factorial is true. And then keep in mind what you want to show. Again, a lot of times I put this in parentheses. Want to show, the BT is want to show that if we add 1 to n, wherever we have n, we have to put n plus 1. We want to show that that's true. And of course, we can make that look a little bit nicer. We can say, or that's true. So this is what we want to show. Once again, usually best to begin with the assumption. And again, let's try to, maybe our first step, try to match either the left-hand side or the right-hand side of what we want to show. Now, it'll probably be fairly easy to match the left-hand side, because if we multiply by 2, we'll get 2n plus 1. So multiply by 2 on both sides. So that's going to be 2, 2n, 2n plus 1 factorial. And so what that's going to mean is going to be 2n plus 1. And so we've matched this side. So let's actually see, what do we have on the right-hand side? Again, we're trying to get to this value, n plus 2. we may have to think about this a little bit, see how we're going to get there. Let's see maybe what we have over here. So remember, n plus 1 factorial means it's to be n plus 1 times n minus 1, n minus 2, all the way down to 1. But what this is the same thing, except starting with n plus 2. Remember, if we had n plus 2 here, then times n plus 1 and n minus 1, then this would be n plus 2 factorial. But we have a 2 here. So now the question is, can we replace 2 with n plus 2? Now, notice a couple of things, that this side here is bigger than or equal to this side. So this is greater than or equal to this side. So if we make this side bigger, it's still going to be greater or equal to that side. And so note that n plus 2 is always going to be greater than or equal to 2, because n is always greater than or equal to 1. In other words, n plus 2, the smallest this could be would be 3, because that's the smallest number. So this n plus 2 is always going to be greater than 2. So note, let me just put this in parentheses, note n plus 2 always greater than 2 for n, long as n is greater than or equal to 1, which is what we have here. So that means if we, that should say note n plus 2 is always greater than 2. So that means if we multiply this by a number that's bigger than 2, this side will still be bigger than that side. So that means we're going to have 2n plus 1 greater than or equal to n plus 2 and plus 1 times n minus 1 and minus 2, like this. And then, of course, what is this? This is n plus 2 factorial, which is what we wanted to show. So that completes the proof. So we showed that this is true for the basis step, and we assumed that that was true for n, and proved that it's true for n plus 1. Now we're going to use mathematical induction to prove that an expression is divisible by a given number or a certain number. And we still use mathematical induction, though sometimes the way we carry it out slightly different than we do for other induction problems. First of all, let's once again just real quickly and review induction. If we want to prove that an expression or a property of natural numbers is true for all n greater than or equal to m, where m and n are natural numbers, we must show first the basis step that the property is true for the first value of n we're given, then prove the induction step. We're allowed to assume it's true for a particular n. It's true for, like, say, a given general n. Assume that that's true, and then show that it's true for n plus 1. That's the normal steps for induction. And we're still going to do that for these problems, divisibility problems. And let's actually go through this and just do some examples. Again, we're mostly in this video going to be focusing on specific problems where you're doing showing something is divisible. Let me just jump right into it. Let's take a problem here. Let's say show 5n minus 1 is divisible by 4 for all n greater than or equal to 1. Once again, for all, that means for all n. So again, do your proof. As always, do your basis step. And that's going to be whatever your first value is here. In this case, it's n equal 1. And so this is going to be, so the question is this divisible by 4? And so that's going to be 5 minus 1, which is 4. Yes. And just as before for the induction step, we're allowed to assume that 5n minus 1 is divisible by 4. And we want to show that if we replace this with n plus 1, is that's divisible by 4. Now, again, everything works the same as in the induction problem. The one difference is that usually for most other types of induction problems, we would start by working with what we're allowed to assume and then try to get to what we want to show. Now, in this case here, usually we'll start with the expression we want to show and then show that this is divisible by 4. So we'll begin with this. Now we can't assume it's divisible by 4, but we can start with this and we want to show that this is divisible by 4. Should begin with this. And then we want to show that this is divisible by 4. And now we're going to be allowed at some point use what we have up here. So let's start with this. We want to show that this is divisible by 4. So let's think of what we have here. What we would like to get, we would like to be able to use our assumption at some point. So, like, for example, we would like to somehow factor this to get 5n minus 1. So let's see what we can do with this. So we could actually, we could pull a 5 out of here. So this would be like 5 times n minus 1. Unfortunately, we can't factor the 5 out because we don't have a 5 here. Now, what if we had a 5 here? We could factor out this 5 and have a 5n minus 1. So what we'd like to do, we'd like to somehow create a 5 here. And the only way to get a 5 here is to subtract 4. Now, this time we're not working with two different sides, so we have to, if we subtract something, we have to add the same amount. So add and subtract 4. So let's do that here. So it'd be 5 and minus 1 minus 4. So we subtracted 4 and then added 4. Okay, we're allowed to, so we just basically added 0, which is what we're allowed to do. Now let's put these two together. So it's be 5 and minus 5 plus 4. So now we can factor a 5 out of here and get this. So if we factor factor a 5 out of here, and we get that. So now we can use our assumption. Remember, we're allowed to assume that this is divisible by 4. So again, if you have two things multiplied together, one of them is divisible by 4, then that whole term is divisible by 4. So this is divisible by 4 per our assumption. And then obviously 4 is divisible by 4. So that proves that this is divisible by 4 because we started with this and chose divisible by 4. And so usually that's one of the tricks that you need to keep in mind is that you want to try to use your assumption. You're going to work with what you're trying to show and then somehow be able to work your assumption into it. And let's see if we can find another one here. Let's try. Try this example here. Show that 3 to the 2n minus 1 is divisible by 8 for each n greater than or equal to 1. So let's do this. For proof, do the basis step and equal 1. Again, we picked that because that was our first value here. And let's see if this is true. So we put 1 in here. So this is gives us 3 squared, which is 9, minus 1, which is 8. And of course, this is, so yes, this is divisible by 8. And do the induction step. 3 to n minus 1. I should, let me write that a little bit better. Assume that's divisible by 8, and want to show remember we have to replace n with n plus 1. Want to show that this is divisible by 8. Or let's maybe clean this up a little bit. Or 3 to the 2n plus 2 is divisible by 8. So, as I said before, when we're doing these divisibility problems, we'll start with what we're trying to show. Start with that expression and show that it is, in fact, divisible by 8. So begin. Again, we can begin with this expression. We can't assume it's divisible by 8, but we can at least begin with this and show it is. Again, though we are allowed to use this up here. So once again, like the last problem, we would like to somehow be able to get a factor out something so we can end up with this expression here. So let's see what we have. So here, so let's just factor this here. This is going to be 3 to n minus 1. And like before, we would like to factor out a 3 squared out of here so that we're left with this. So we need here, like the last part, we need a 3 squared, need 3 squared or 9 here, right? So we're going to have to, so if we have a -1 here, to get a 9 here, we're going to have to subtract 8. So add and subtract 8. Like this. And then we put these together, will give us 9 or 3 squared. And again, we were allowed to do this step because we added 0, in fact, because we added 8 and subtracted 8. So now we have this expression. Now we can factor out the 3 squared. Give us this. And again, the reason we wanted to get to this because we were allowed to assume that this is divisible by 8. And of course, if you have two things multiplied, one divisible by 8, the whole term is divisible by 8. And this is divisible by 8, obviously. And so that's what we wanted to prove. And let me do one more example. I want to show this is divisible by 6 for each n greater than or equal to 1. And do the basis step. Once again, it's wherever our starting point is. And equal 1. So assume this is divisible by 6. And want to show that if we replace n with n plus 1, this time it gets a little bit more complicated. That this is divisible by 8. Excuse me, divisible by 6, excuse me. So let's begin with this. We're going to have to maybe multiply things out a little bit here. So this is going to be n plus 1. And over here, this will be n squared. And then when you do the foiling, it's going to be what? 2n plus 1. But then we have a plus 5. This is going to be 6. You can verify that for yourself. Now let's multiply this out. So this is going to be n cubed. I'll take n times each of these, plus 2n squared, plus 6n. So I took n times each of these. Now I'll take 1 times each of those. N squared plus 2n plus 6. And then let's sort of combine terms. What are we going to have? This is going to be n cubed plus, what that's going to be 3n squared. I put the n squareds together. Plus let's see, be sure I don't mess something up here. And then, so if we put, this together, give us 8n plus 6. And again, think of our assumption. Keep our assumption in mind up here. We have like an n cubed plus 5n. So keep assumption in mind. So let's think what we have. Let's rearrange this so we can maybe get something that kind of looks like our assumption. So n cubed plus 8n plus 3n squared plus 6. So again, if you keep the assumption in mind, we really need a 5n here, don't we? So add and subtract 3n. So 3n cubed. So let's subtract 3n and add 3n. And then just bring the other stuff down. Like this. So now over here, then we're going to have 5n. And then over here, again, I put those together. Let me rearrange this a little bit. 3n squared plus 3n plus 6. Now let's factor out an n out of this. Again, that'll give us our assumption. Remember, by assumption, we can say that's divisible by 6. Now, what about over here? Let's factor out a 3. We get this. Now, this we're going to have to be a little bit creative over here. Let's see. If we could show that this is an even number, then 3 times any even number has to be divisible by 6. And so let's just carry this down one more. And let's notice that this has to be an even number, this right here, because this has got to be n times n plus 1. I just factored these two terms like this. So again, this has to be an even number because this would be like 2 times 3 is 6. 3 times 4 is 12. 4 times 5 is 20. 5 times 6 is 30. So this is going to be even. Even. And so 3 times an even number is divisible by 6. And then over here, this is divisible by 6 per our assumption. And so we're done. This one took a little bit more work. As before, we're always looking to start with what we want to show is divisible, and then try to work in our assumption somewhere. So when we got to this point here, we knew we wanted to get this in here somewhere. So that's why we rearranged this a little bit. But we needed a 5n here instead of an 8n, so we had to subtract and add 3n. That gave us our 5n here. And we put 3n over here. And now over here was our assumption. So we're allowed to assume that's divisible by 6. Over here, we had to work with this a little bit to show that this is divisible by 6.